Welcome to chapter 14. This slide was in here, and I just thought I would leave it on here because I haven't, just it kind of shows me my life. So if you don't know me, this is me cross-country skiing. This is my husband. These are my two stepchildren. One of them is actually at school at EKU this senior year, and then this is my daughter Sarah Ferguson, and she is pole vaulting now at the University of Washington. So just a little intro there. All right, so which structure is compound B? So this is a resonance structure review question, and you see that this pi bond moves there, and then with that curved arrow, and so then the electrons, you go there, this goes here, and now you get your carbocation, and then you have another one curved arrow that gives you compound C. So the answer would be C. All right, so this is another review question from chapter 13, and you see H nu and light. You might see that as HV. This is the initiation step where the bromine with H nu generates a free radical, so that's homolytic cleavage to get this. And then your propagation step where you would take your alkane, so this is alkane, and you would do a hydrogen abstraction. The question is which hydrogen would be extracted. This hydrogen would be the hydrogen extracted because that would give you a tertiary radical. There's no rearrangements, but that's going to be the hydrogen that's the easiest to abstract, and then that's HBr. So that's propagation step 1. Propagation step 2 then would be this free radical here, and reacts with another molecule of bromine to generate the product, which is C plus another radical. So C is your answer. What is the major product of the reaction below? Okay, so in this case, you don't have any hydrogen peroxides or anything like that. So this is electrophilic addition, and you're going to get the bromonium 3-membered ring cation, and then, well, that goes there and that goes there. And I wouldn't even actually do any electron flow arrows for this. So you make your bromonium, and then remember this is going to do anti-addition. This is going to attack at this carbon because the bromonium is positive charge, and that's going to give you an anti-addition of the bromine. And there you go. So A is your answer. Okay, and then we have review of allylic bromination with MBS. This is MBS. This is a source with H nu. This is a source of initiation of bromine. We have an allylic proton. That's going to be the proton that gets abstracted. Propagation step 1. Then propagation step 2 will cause the bromination of the allylic bromination. This is still a review, so we'll move on. Formation, so this is review, and this is review. So radical versus ionic. This is ionic addition, electrophilic addition, and then MBS or peroxide generates the free radical that becomes allylic bromination. All right, now This is where we're going to start today, chapter 14. Conjugation. So conjugation is something you need to be aware of. It occurs whenever you have p orbitals that overlap 3 or more adjacent atoms. So here this is a sp2 carbon, sp2 carbon, sp2 carbon, sp2 carbon. And so what happens is there's these, this is all planar, so it's flat like a piece of paper, and then above and below the plane are these unhybridized p orbitals. And they overlap, so they're kind of like a almost like a wire. This is an sp2, this is sp2, and a carbocation is sp2. So this has unhybridized p orbitals as well, allylic carbocation. So how can you find a conjugation system with these sp2, sp2, sp2 carbons? Is if you have alternating double, single, double, single bonds. And there you go, you can see the overlap. What happens is this overlap allows for the delocalization of these electrons, and it's very stabilizing, making it more stable, lower energy. Dienes, so these are dienes. This is, you need to be able to, I can classify compounds as either conjugated, non-conjugated. That would be like an isolated diene. So here's a conjugated diene. You got sp2, 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 sp2. This one is sp2, sp2, but then it's separated by an sp3 and an sp2, sp2. So this is localized, they're not delocalized, and this sp3 carbon prevents this unhybridized p orbital overlap. So that would be higher in energy. So the allylic carbocation is an example of a conjugated system. And this is showing you that because this is sp2, 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 and those electrons. This is a double-headed arrow for resonance. Shows you that these are the same thing. And so you have lower stability. You have more stability. You have, lower energy, more stability when you have conjugation. So allylic cation is going to be pretty stable. I always consider it about the same stability as a tertiary carbocation. This is just showing you, sometimes you'll see a halogen and they have larger orbitals and they can delocalize these electrons next door. So if you have a next door neighbor that's sp2, then those electrons can go there. And so this is the allylic system. You have already been introduced to this in Organic 1, where these are resonance structures. And then here we have an acetate anion, which this is an sp2, 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 and so those electrons can do a resonance structure there. And that's an example of oxygen, not carbon. So resonance is this delocalization. You've seen also aromatic molecules. They have really lower energy. So these are really stable. And these alternate double single bonds. If it's aromatic, it's also cyclic here. And we'll talk about criteria for aromatic compounds. Here, these are sp2. So you see the double, single, double bonds. And those are conjugated. All right, so which structure is the major contributor in the resonance structures below? So when you look at these resonance, this doesn't have a positive charge. So that is concerning. When you're doing these, you need to go ahead and put in all your lone pairs to make it right. So here. So if you have this here, this could go here and that could go there. That would be an example of a correct Lewis structure. This is not the same here, and this is not. This is missing a positive charge. So I would say C, because you have, these are correct resonance structures, and then you have your negative charge on your more electronegative atom. Okay, so we've been doing resonance structures, so this should look familiar. They're just talking about the rules, which are better resonance structures. They have more bonds, fewer charges. Every atom needs an octet. That's going to be a better one. So here, this is a carbon with 6 electrons. This is a carbon with 8 electrons. So this would be a better resonance structure because every element has a complete octet. And here, this is a negative carbon, and those electrons are going to stabilize. This is going to be better because the negative charge on the more electronegative oxygen is going to be lower energy. Here, this is showing you carbon anions, and this is going to be better because, one, you got the negative charge on the carbon instead on the oxygen instead of the carbon, and you have more bonds. It's like the same bonds. They're showing you that this is sp2 hybridized. This is an sp2 hybridized. So you don't count the lone pair as a thing because the next door neighbor is sp2. So here you can see that that's sp2, sp2, and then this oxygen would also be sp2 because it can do resonance. So p orbitals are required for conjugation. That's why they have to be sp2. If you have an s orbital and the p orbital, px, py, and pz. If you have an sp2 orbital, then you've taken the s, you've taken 2 of these p orbitals, and that leaves you with an unhybridized p orbital. And you have to have that in order to have conjugation, and they need to be next to each other. This is showing you that conjugated dienes are kind of how to name them, and they are very stable. So here's sp2, 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 sp2. See double, single, double bonds. These are trans. And since you have 2 of them, there's EE for trans, and then you have to do it's a diene. Here, this is cis, and this is cis. So there's your ZZ13 diene. This is cis and trans, so you're going to get Z and E for cis and trans. These are diastereomers. You do get bond rotation around the single bond. So these are conformers, and this S-cis means S is for the sigma bond. So this is where the double bonds are on the same side. That's an S-cis conformation. Here, with the double bonds, are opposite side, that's S-trans. This can happen, so they are able to rotate. That's going to be important for the Diels-Alder reaction. So they're able to rotate around a single bond, a sigma bond, a single bond, sigma or single bond. So you can interchange between these two conformations. This stereoisomer cis-cis, so ZZ and trans EE, they're diastereomers. These are okay, so they're just showing you that these are actually just 2 conformations. They're the same compound, same name. All right, so conjugation, increased conjugation, you get into the visible. So if you have like oxygen and double bonds and carbon dioxide, the double bonds, and aromatic. These are all, they absorb UV rays. Okay, they absorb UV, but then that's ultraviolet, so that's before violet. Okay, so in the electromagnetic spectrum, violet is a color, purple. Okay, but then you get more, and then you got Roy G. Biv. Roy G. Biv. Roy G. Biv. So this is violet. This is orange. This is red. And so if you keep the, see how we got a double bond here? These are all UV, ultraviolet. So they're before violet. They're up here, absorbing. But if you keep getting the conjugation, you can get into the visible. And this is lycopene. It has 11 conjugated bonds, and it's actually the red color of tomatoes. This is a conjugated system here. Double, single, double bonds for Zocor. Here's another conjugated system in calcitrol, which manages the calcium levels in the blood. Okay, which statement is correct regarding the structures below? Compounds A, B, and C are conjugated systems only. This is an allene, and so this is sp2, this is sp, this is sp2, so that would be conjugated. It has unhybridized p orbitals. This is sp2, 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 so that's conjugated. This is sp2, 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 so that's conjugated. This one is sp2, sp2, then we have an sp3 that breaks this up, so this is isolated. So D is an isolated system only, yes. B and C are both correct. Compounds B and C are conjugated systems. A, B, and C are conjugated systems only. I would consider B and C correct, so I would go with B and C are both correct. Okay, figures of conjugated features. This is a shorter bond. It's not really a single bond. You see it's 153 picometers. This is just the length. Here it shortens, so you get a shorter single bond. And conjugated dienes absorb longer wavelengths of ultraviolet light. So if you get a lot of conjugation, you even get into the visible. That's the electromagnetic spectrum. They're just showing you why you have a shorter bond here. It's because you have more S character. This is showing you that conjugated dienes are more stable. So basically you're going to this pentane. So this is pentane. So pentane has a certain energy. So if you go to the same final compound, and this has the same energy, so if you have your reaction energy diagram, so you're going to have pentane here at a certain energy level. Then what's the energy difference between these two? Well, this one here would have a higher energy because it would go to that energy, so that's 255 compared to this one, which is conjugated, and it would have less of an energy to go to the same product. So this is going to be more stable starting material. It's going to be lower energy. More stable is lower energy. So here's your energy diagram, and there's your lower energy. So the starting energy is going to be less. This is a catalytic hydrogenation. You know that converts alkenes to alkanes. It's a reduction. So the stability is about 7 kilojoules per mole for conjugated diene compared to isolated diene. And so this is showing you isolated. Now you're going to get different kinds of reactions. You just need to keep in mind, you need to do the resonance structures. So here you do hydrobromination, and so when you do that, the hydrogen adds here. Oh, we got 5. Let's get 5 carbons here. Hydrogen adds there, and then the bromide will then add there, and you get the HBr. You could have picked the other one. One equivalence. But here, this is isolated. But here, when this happens, you get this intermediate. Okay, and then so the bromine can add there. So you can have a bromide that adds there. And then you get something like, this is called a 1,2 addition because the hydrogen adds at the 1 and the bromide adds at the 2. Or you can get a resonance structure where once you add your hydrogen at the 1, the double bond goes there, and then the bromide adds here at the carbon 4. This is a 1,4 addition. So you see 1,2 versus 1,4. And this is going to be important because I'll say, well, this undergoes a 1,2 addition, or this undergoes a 1,4 addition. If it undergoes a 1,4 addition, you get the addition of your electrophile first to get a carbocation that undergoes resonance before the addition of your next nucleophile. So this is showing you that mechanism that we just did. This is when the bromide comes in here, this is going to be a 1,2 addition. Here, this is showing you the bromide coming in after the resonance structure, and then that's a 1,4 product. Okay, so let's look at this. Low temperatures, so cold, negative 80 degrees, you get 80% of the 1,2 product. So this is considered kinetic product. And kinetic product is also, aka, also known as the 1,2 product. And you have to do it at cold temperatures. If you heat it up, so 25 degrees Celsius is room temperature, so you add a little bit of heat here, you get 80% of the 1,4 product. And this is called your thermodynamic product. Okay, and thermodynamic is aka the 1,4 product. And you are expected to know that because I asked you for the major organic product. And so you need to know the difference between kinetic versus thermodynamic. So here, low temperatures, 1,2 addition, higher temperatures, 1,4. And see, there we go. This is the kinetic product, major product at low temperatures. This is your thermodynamic product, major product at the higher temperatures. So this is how it's happening. This is the how/why. So, okay, so let's say this is your thermodynamic product here. See, the thermodynamic product is lower. See, it's lower energy. This is your kinetic product. This is kinetic. You see it's a higher energy. So if you look at the energy numbers here versus the energy numbers here, you'll see that it's higher energy, this kinetic product. So when you look at the reaction energy diagram, in order to make your kinetic energy, it goes through a lower activation energy. And this is the speed. This is how fast. This one's going to be faster. And that's why if you can do it at colder temperatures, the transition state does not have to go all the way to the top here. So this one takes slower reaction. This is your thermodynamic. You got to climb the tallest mountain. So faster is going to be your kinetic. Slower is going to be your thermodynamic. And you can do that. You can control it by the temperature. So you can see that this is an internal di-substituted alkene. It's more stable. So that's going to be your thermodynamic product, and you added a 1,4 addition. And this is just showing you that the transition states are going to be different. So here we have the kinetic product is going to be this lower energy. So it's because this activation energy here is lower. And that's what makes it kinetic. It'll happen faster. So the height of this activation energy is the speed of how fast a reaction will go. This height here is higher. So it's going to be slower, but it will give you your thermodynamic product. So you can basically heat these, just warm them overnight, and your reaction, the longer it goes, with a little bit of heat, you can get your thermodynamic product. But you're in the lab and you want your faster one, you're probably only going to do the reaction for about 15 minutes, and you're going to do it like at negative 80 degrees Celsius. So this is not something you want to let go for long periods of time if you need to get that kinetic product. And you'll see this in a lot of different reactions. Okay, so here, what is the major kinetic product? So you got to read this. Kinetic means 1, 2. So you're going to basically get this intermediate where hydrogen's going to add to the 1. You get your carbocation, and then the bromide will add to the 2 position. So if it's a kinetic product here, do H there and Br there. And that would be 1, 2, that would be C. All right, so that's that. Now, what about the Diels-Alder reaction? Here's the Diels-Alder. It's named after Diels, which is a scientist in Germany, and Alder as well. And you also have a POGIL exercise for the Diels-Alder. So this is a important reaction, and the POGIL exercise is very helpful. I do want you to label on all of your mechanisms for this. You need to label the diene and the dienophile. So either one of them is going to be the diene, one of them is going to be the dienophile. The diene has a double, single, double bond, hence the diene, and it reacts with the dienophile. Ophile means love. So this dienophile loves the diene. Okay, so that's what that means here. So this is just a dienophile. Now, this is called a paracyclic mechanism. You haven't had a paracyclic reaction mechanism yet. Okay, so this is paracyclic. So this reaction mechanism is you need 3 curved arrows. Okay, so you need 3 curved arrows because it's concerted. So that goes to this carbon here. This double bond goes to that carbon. This double bond goes here. That's what that means, double-headed arrow. And then this double bond is going to go to that carbon. So we have 3 curved arrows. It's concerted. So it's like a concert where you got clarinets playing at the same time the drums are playing. So these bonds are all breaking and making at the same time. The other thing I want to see you do on your reaction mechanisms is I want you to label the carbons as 1, 2, 3, 4, 5, 6, because you always, remember if I say always, you want to write that down, always get a 6-membered ring with a new double bond formed. Okay? So here we have the double bond formed, and there's your 6-membered ring. 1, 2, 3, 4, 5, 6. And so I want you to line these up, label them, have your 6 curved arrows, and then number them also in your product. This is a concerted process. So 3 pi bonds and 2 sigma bonds are 3 pi bonds are breaking. So we got to total up to 3. We have 3. So 3 pi bonds are breaking. So we got to have a 3 being made. We're getting 2 sigma bonds. That's 2 plus 1 pi bond. So that's 3 bonds. The new sigma bond is about 20 kilocalories stronger than the pi bond. So this is exothermic. It releases 40 kilocalorie per mole of energy. Okay, so here we have the labeling. We have the diene. We have the dienophile. Now there's like four things you need to pay attention to on the Diels-Alder reaction, okay? And so the POGIL does a good job with the models going through these 4 things. And we're going to bring those to our attention here. And the 4 things don't have so much to do with this. You still label diene, you have a dienophile, you have the, I want to see the numbering. So let's number 1, 2, 3, 4. Your POGIL does that. 5, 6. Your book doesn't, but I want to see it. 3, 4, 5, 6. That way you can, and then you have your 3 curved arrows in your mechanism. Now keep in mind these are all flat, right? They're conjugated. These are all flat. So this pi bond goes here. That pi bond goes there. This pi bond goes there. And so we have 3 pi bonds being broken. 3 pi bonds broken. And then we have 1 pi bond made plus 2 sigma bonds made. And you can see those right there. A lot of times you just need heat. This is an example of this Japanese pufferfish has this tetrodotoxin. It's a natural product that has several 6-membered rings together. It's isolated from the ovaries and liver of the pufferfish. But it was made, this step here, in a Diels-Alder. So you can see that this is your diene. And there's 1, 2, 3, 4. And then you have your dienophile. And so that's 5, 6. And then you have your 3 curved arrows. Make sure they actually point to what it needs to point to. And then you have your 1, 2, 3, 4, 5, 6 membered ring with the double bond as your product. So when you get a reaction like this, you need to draw them lined up. So I would take this diene, I'd find the diene and draw it first, and you're going to have to rotate this around the S and make an S-cis conformation to this, okay? And I want you to then, this is problem solving. So you get this reaction, you're like, okay, now I got to do my work. This is my work that I do on the scrap paper. I'm going to draw that first. I'm going to label it. I'm going to see that's my diene. And then I'm going to take this compound here and be like, okay, that's my dienophile. And then you can draw it like this, but that's 5 and 6. And then you can draw your curved arrows. And make sure that points to that carbon. This double bond points to there. This double bond points to carbon number 5. And then you can draw it with your 6-membered ring. Your double bond there, 1, 2, 3, 4, 5, 6, and you see that this is your double bond between the 2 and the 3, and then make sure you look at each carbon and make sure that obviously you need to draw in on your 6 carbon this portion here. And so that is the Diels-Alder product. So see how the diene and the dienophile are lined up. You got your curved arrows, and I would go further to even number these. And then here we're numbering and make sure that you add on this substituent off of that 6th carbon. So that's the first thing. Now, remember I said there were 4 things. 4 things you need to consider when you're doing the Diels-Alder reaction. One of the things is this right here. The diene can only react if it adopts the S-cis conformation. Because what's happening is this is a concerted reaction, and these pi bonds have to line up. So you're going to have to rotate this into the S-cis conformation. And so, like I said, you've got a nice POGIL around this, because you're going to find that some rotations are prevented by cyclic alkenes. And if they can't get into this S-cis conformation, then you're going to have no reaction. So this is the first thing of the 4 things to consider. And then you can see that this is the speed of the reaction will determine this. This is a cyclopentadiene. This is cyclopentadiene, and it's already in the S conformation, so it's very reactive. This compound here is never going to be able to get into the, it's in the S trans, it's locked in, we call that locked in. That conformation is locked in. So it cannot rotate around this double bond because of the ring, so it's not going to have a reaction. So in a Diels-Alder, this is unreactive. This is one of your POGIL questions. Which diene reacts the fastest in the Diels-Alder? Obviously, it's going to be B because this is already locked into the S-cis. Okay, this cannot. This is S-trans. This will not, no reaction. And then these here can rotate. And if I had to rank them, I would say C reacts faster than D, because I would say B is the fastest, then C, and then D. Because you just have to carry this to rotate, so. And practice that, right? So write the diene, this would be that compound there. Okay, so that was rule number 1. Rule number 2 of the 4 is the electron withdrawing substituents on the dienophile. So now we're talking about the dienophile. This needs to have electron withdrawing. So electron, like methyl groups, are electron donating groups. So they're going to put electron density in. Electron withdrawing groups are like carbonyl. So any carbonyl or a nitro, because of the positive charge on the nitrogen, these are electron withdrawing groups. And you see that that's going to make the reaction rate increase. And so they're saying this generic Z, if it's electron withdrawing, the reactivity of the dienophile is going to increase. So when you look at these, if you do the resonance structure here, you could see that this resonance structure, let me try to draw this a bit better. You can see that a carbonyl puts a slight positive charge on that carbon. So that would definitely be electron withdrawing. So a positive charge pulls that electron density towards itself. So this is a carbonyl, and like I said, that could do a delta positive. So benzoquinone, this is a very reactive dienophile. Here we have another carbonyl. These are all examples of excellent dienophiles because of the carbonyl. Okay, so that's rule number 2 about the dienophile. This is rule number 3, and it's the stereochemistry of the dienophile. So we're still talking dienophile, is retained. So you see here that this is a cis. You see that's a cis dienophile. So then you've got to show the cis here. So you can pick both dashes or both wedges. You get to choose, but I need to see that the stereochemistry on your dienophile, if you have a cis dienophile, that you maintain as a cis. If you have a trans dienophile, then I need you to show that by picking dashes and wedges that are indicative of a trans product. They're showing you a bicyclic compound here. So let's look at this. So this is your diene, and we're going to number that. It's in the S cis conformation, so we're good. And then this is your dienophile. And now we're going to do our curved arrows. That's going to go to the 1. It's going to go here. This is going to go to the 5. And then when you draw your 6-membered ring right here, 1, 2, 3, 4, 5, 6. This is a bicyclic product because you have 2 of these rings are sharing this bond here. And so these are going to go, it's going to be cis fused. So you see how both of those are indicated with the wedges. This is a bridge system here. So this is a bridge. We have the diene, we have the dienophile. Now keep in mind here that so there's 4, 5, 6. On carbon number 1 and carbon number 4, you have this CH2 here. This is 1, 2, 3, 4, 5, 6. Carbon number 1 and carbon number 4, you have this carbon here, and that's the bridge. And so if you were to draw this like so, this compound, this CH2 here, is this right here. And this is your double bond. And this is a bridge cyclic ring. So in the bridgehead carbons, it's called bridgehead carbons. Carbons are right here. So you can get fused rings and you can get a bridge cyclic system. So you need to, that makes this kind of hard sometimes. Okay, and this is the 4th factor that you need to consider. Like I said, your POGIL does a good job with all that. So here we have our diene and we have our dienophile, and you number them 1, 2, 3, 3, 4, 5, 6. You've got your 3 curved arrows, and then it's always 6-membered ring. Okay, this here becomes that right there. This carbon here, this carbon CH2 here is this carbon. So where's your 1, 2, 3, 4, 4, 5, 6, and then you have the Z, and the Z is endo. So this is endo, which is kind of axial down, and then you have your hydrogen right here, which is exo. And so this is the preferred product. So when these come together, the Z wants to, and remember this is electron withdrawing groups, okay? So this is kind of like a delta positive. And it wants to kind of hang out underneath here next to these pi electrons. And so it's electronically attracted to this negative electron. And that's why you get the preferred endo. So when you're drawing these, you need to consider that the endo is the preferred energetically favored arrangement. And this is showing you why. And like I said, this is kind of delta positive because it's on the dienophile. And the dienophile likes electron withdrawing groups. And so that positive is going to be really attracted to that negative environment. And so when it lines up, and this is concerted. So what's happening is the molecule has to line up with these unhybridized p orbitals. And these unhybridized p orbitals, they have to snap into place, okay? And when I think of snap into place, I think of like IKEA furniture. If you've ever had the joy of putting the IKEA furniture together, you got to line it up and it snaps. Legos. So, and that's one of these reasons why you get the endo. All right, there's actually one other thing that I need to tell you that it's going to come up, so we'll see. This is your dienophile. This is your diene. The diene is in the S trans, so we're going to have to rotate that. That's the first thing we need to do. So we're going to rotate that like so. And then we're going to do 1, 2, 3, 4. And then we have our dienophile. And then we're going to do our curved arrows. Carbon number 5, carbon number 6. And this is our diene. This is our dienophile. And then when they come together, we make 6-membered ring with a double bond there. 1, 2, 3, 4, 5, 6. And then we're going to make sure that we get whatever's coming off. So of the 1 we have, or off of the 2 we have this methyl group, so we're going to do that there. And then off of this 6 we have this nitro, NO2. I don't have to worry about cis and trans here because this does not have cis and trans isomerism. Now, the question is this the product? We'll say this is product A. This is what I have to teach you. Or is it product B? What is product B? Product B would be this one. So here we take the diene, but then we got to flip our dienophile. So 1, 2, 3, 4, 5, 6. And then we get the curved arrows. So we get our 6-membered ring. This one's product B. We get that there. 1, 2, 3, 4, 5, 6. And now we've got this methyl coming off at the 2. And we have the nitro now coming off at the 5. Okay, and I'm going to tell you product B is your major product. And this is your major. Now why is that? And we're going to learn this in the next chapter. The substituents here are 1, 2, 3. They're like a 1, 4 apart from each other. And you're going to learn in nomenclature that's para. So if you have 1, 4 disubstituents on a ring, which will be aromatic ring, that's considered para. If it's 1, 2, it's ortho. And so you're going to find that ortho and para products actually make products. This would be a 1, 3. 1, 2, 3. This would be a 1, 3. That's called a meta. And meta does not happen for the Diels-Alder. So your product here needs to be a 1, 4 substituted compound. So there's your major product. Okay, so here we have the diene. 1, 2, 3, 4, and this is your dienophile. 5, 6. We have our curved arrows here. And so we're going to get our 6-membered ring. Now we have a double bond here, right? But then we still have a double bond here. And let's number them 1, 2, 3, 4, 5, 6. And we also have the CN coming off. And we don't have to worry about dashes and wedges because you have a double bond there. Those are sp2 carbons. So they don't have dashes and wedges. So then you find your product and you see that it's B. Okay, so retrosynthesis analysis, we introduced this in Organic 1 when we think things backwards. So if you ever see a six-membered ring, like so, you get something like this, then you need to be able to do these retrosynthetic arrows and be like, okay, um, you would want to be able to number this, and you'd want to put an X between the 1 and the 6, the 4 and the 5. Okay, and so you put X's there. Those are the ones that are broken. So you could see that this is these two here are going to be your diene and dienophile. So retrosynthesis, how would you do this? You'd number 1, 2, 3, 4, 5, 6. Put an X between the 1 and the 6 and the 4 and the 5. And then what would that be? That would be your diene, 1, 2, 3, 4. And then your 5, 6 would be NO2. So that would be 5 and 6. Same here. 1, 2, 3, 4, 5, 6. Put an X between the 1 and the 6 and the 4 and the 5. And then draw your retrosynthetic arrows. And this would be your diene. 1, 2. Make sure you get your methyl there. 3, 4. 1, 2, 3, 4. And then your 5, 6. That's going to be a triple bond. CO2 methyl. And then CO2 methyl. And I think that's what they're showing you here. You can see doing it this way, or you can just do the way I did it with numbering and the X's here. So 1, 2, 3, 4, 5, 6. There you go. Here 1, 2, 3, 3, 4, 5, 6. That would be with the bridgehead. Do you see the CH2? Is that CH2? And then the 5, 6 here. So there's 6. 5 is Cl, and then you have this CO ethyl dienophile. Okay, the reason why Diels-Alder is such a big deal, Diels-Alder got a Nobel Prize for this work, for this reaction, is because you get six-membered rings. And where do you see six-membered rings? You see them in the steroid skeleton. So steroids are your estrogens, your testosterones, a lot of your hormones. They have this six-membered, 3 six-membered rings, and then they have this 5-membered D ring. And the generic ways is A, B, C, and G. And so this is a nice way to make six-membered rings. This is one of the reasons why we were able to get into synthetic compounds of cortisone and estrone and cholesterol. We can synthesize unnatural steroids. This is showing you got a dienophile and a diene here, and you can put in the C ring. This is the C ring, and then you can reduce that with catalytic hydrogenation. Here, this is the maybe the B ring here. So this is your B ring. The B ring is established here. Okay, which dienophile is reactive for the synthesis of the product below? So let's number these, our six-membered ring. Let's put our X's here. So we're going to think retrosynthetically. And then this is going to be, do you see the oxygen here? So that's the 1, 2, 3, 4. This is your diene. And then so your dienophile is right here. Make that a double bond. And then do you see how they're on the same side? So this carboxylic ester acid need to be cis because you got cis here. Now it asks for the dienophile. So this is your dienophile. So this is um, D. And notice it's cis, not trans. And that should wrap up this chapter.